So 2.6 graphs of rational functions. So definition, rational functions let f and g be polynomial functions with g of x not equal to 0. Then the function given by r of x, okay, symbolizing rational function, is equal to f of x over g of x is a rational function. So r of x just symbolizes that's going to be a rational function. So kind of going to do a little example here within this, but if you had something that says find the domain and use limits to find end behavior at the value or values of x not in the domain for something like f of x is equal to 2 over x minus 3. Then to find our domain, we're looking for what x values make it true. The only thing that cannot be true or cannot occur with this one is that the denominator cannot equal 0. So I would set x minus 3 equal to 0, so x equals 3. So where x equals 3, it does not exist. So the correct way to write domain is from negative infinity to 3 union 3 to infinity. And then we're going to throw it back a little bit to vertical and horizontal asymptotes. So your vertical asymptote, remember it's also where the denominator is equal to 0, would be at x is equal to 3. And then your horizontal asymptote, you're going back to your clown poem. So if it's bigger on top, there is none. If they're both the same as the coefficient, if it's bigger on bottom, y is equal to 0, which is the case that we have because we only have an x on the bottom. So y equals 0. So then what this wants us to do is talk about what's happening at the point, okay, where it doesn't exist when it's talking about limits. I think we've done a little bit with this before, but the limit as x approaches 3, and when it's got the little minus sign in top, that means from the left. So as we get to 3 from the left, so something like 2.99999, what happens to f of x? So I've got 2 divided by 2.99999 minus 3. Okay, so that's something like 0.0000001. Okay, and that's negative, so 2 divided by that. 2 divided by a really small number is going to give us a really big number, but it's negative, so that's going to give us negative infinity. And then if we did the same thing from the other side, the limit as x approaches 3 raised to the little plus sign, that means from the right of f of x, we're looking at a number like 3.0000001. Okay, and then minus 3 is giving you that 0.00001 on the bottom. So 2 divided by essentially a really small number gives you a really big number, and it's positive, so that's giving you infinity. Loose hair. All right, and then just to talk a little bit about in behavior in terms of looking at the asymptotes. Okay, that's just kind of an example of where we're going, but now to make this hopefully make a little bit more sense. Vertical asymptotes for in behavior. Okay, we've got a vertical asymptote at x is equal to a. Then what we do is we look at the limit as x approaches a from the left of f of x, and that's going to either be equal to positive or negative infinity. And then we would also do the same from the right. So the limit as x approaches a from the right of f of x is going to be equal to positive or negative infinity. So those answers are always going to be positive or negative infinity when I'm asking about in behavior at a point. Okay. If on the flip side, I'm asking about in behavior at what's happening at infinity or negative infinity, we're looking at the horizontal asymptotes for in behavior, and those occur at y is equal to b, so wherever that is. Then what happens is we have the limit as x approaches negative infinity of f of x, and that's going to be equal to b. And then we have the limit as x approaches infinity of f of x, and that's also going to be equal to b. So horizontal asymptote in behavior is going to be the limits at infinity, and it's going to give you a point. The other ones are you're looking at the limit at a point, and it's going to give you either positive or negative infinity. All right, so moving on, we're going to look at the graph of a rational function.
You're doing pre-cal, guys.
Brooke's popping in to say hello, guys.
Hello.
The graph of y is equal to f of x over g of x is equal to a sub n x to the n plus dot 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 all the way out to what we normally have divided by b sub m x to the m plus dot 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 all the way out to what we normally have. Okay, that super long thing that I normally write out that I never want to have to write again, but it never fails that I do. Has the following characteristics.
Did return.
So there's going to be 4 of them, and then there's going to be some stuff under each one of them. So the first one is in behavior asymptote. So if n is less than m, okay, notice those are the powers that x is being raised to. The in behavior asymptote is the horizontal asymptote y equals 0. So it was bigger on the bottom, meaning y equals 0. Okay, so these are basically a fancier way of saying what you should know from your clown poem.
Huh?
If n is equal to m, the in behavior asymptote is the quotient polynomial function oh no. 1 second, I got it back up. Yeah. can't read apparently, is the horizontal asymptote y equals a sub n over b sub m, so it's the leading coefficients. So if they're both the same, it's the coefficient. And then now, the one that I was just trying to write, if n is greater than m, the n behavior asymptote is the quotient polynomial function y is equal to q of x, where f of x, oops, need more space, f of x is equal to g of x times q of x plus r of x. So there's no horizontal asymptote. So I think the phrase is something like bigger on top. No, there's not, or something like that. So again, if you remember your clown poem, you don't have to really, you can pretty much just ignore what I just said because you already know it.
Pre-cal learned about clowns,
I
guys.
assume this will all make a lot more sense when we're doing stuff.
Yeah, and don't let it scare you. We're not actually graphing stuff. We're just finding information about graphs. So then, vertical asymptotes.
I don't know what purple I was using. Oh, it's this one.
You can also save colors if you wanted to know that.
What really? Do that again? What?
You just hit the plus sign and you can save the color that you're using.
I didn't know they had that. Oh, I wish we did that earlier. I did the little thing where you can like put it over the color, like the little dropper, and then so use the same color. I didn't.
All right, so vertical asymptotes. So these occur at the real zeros of the denominator.
What about fake zeros? Don't you guys wish you had me in pre-cal?
Be a lot more lively.
It's true.
Provided that the zeros
I'm just too focused.
are not also zeros of the numerator or equal or greater in multiplicity. So remember, that's just how many times they occur. Okay, so again, vertical asymptotes, you know, it's at the denominator equal to 0. And as long as they're real zeros, okay, so as long as they're not like i's and imaginary stuff, then it's a vertical asymptote. Three x-intercepts. These occur at the real zeros of the numerator so set the numerator equal to 0 and solve for it. Specifically ones which are not also zeros of the denominator. So x-intercepts, there's another way to think about it is setting y equal to 0 and solving for x. And then the fourth thing we're going to have are the y-intercepts, which is, this is the value of f of 0 if defined. So we said for x-intercepts, you set y equal to 0, solve for x. For y-intercepts, set x equal to 0, solve for y. There's one more little condition here that's something completely new that you would not have seen to this point. If the end behavior asymptote of a rational function is a slant line, we call it a slant asymptote or oblique asymptote. I can't remember if your book actually has you finding them, or if it will actually end up giving you any that are oblique. Does not look like it.
That's good, right?
So yeah, I had one of the teachers I worked with at Bethel High School. Their book required that you find oblique asymptotes, and so they're not hard to find. They're just different. They're not like as simple as just setting the denominator equal to 0 or something like that. And it's one of those things that I don't even remember doing in high school. I might have vaguely remembered doing it, but it was one of the things where I had only really seen it with him. But your book does point out the fact that they do exist. I just don't think that there's any scenarios where you actually have to find them in your book.